Okay, let's come back and we continue our lecture by analyzing what happens when you want to override function. So we have seen already that you can define function with the same name. Okay, so basically there are two things you can do. You can overload and you can override. So overloading means you have a different function with the same name, and this has nothing to do with the virtual function mechanism with the dynamic binding. This is just another function with a different name. And then you have overriding. Overriding means you define a virtual function in a derived class, which must have, of course, the same prototype as the virtual function in the base class. So the prototype of the two must be the same. And for example, you cannot change the return value for sure, because the compiler will not know which function to actually call. Okay? And remember that if you change anything else, like parameters, for C++ is actually a different function. So you are not overriding, you are overloading. That means you are defining a different function with the same prototype. So be careful when you want to write a derived class and you want to define a virtual function. The virtual function must have exactly the same prototype with the same parameter list as in the base class. There is only one exception to the previous rule. If the base class virtual method returns a pointer or a reference to an object of the base class, the derived class can change the return value to a pointer or reference to an object of the derived class. So for example, you can have class A, which defines a function f virtual, which returns a reference to an object of type A. And then you can have class B, which derives from A, that returns a reference to an object of type B. And this is okay, because in class A you are returning a reference to an object of class A. In class B you are returning a reference to an object of class B. So this is actually the same function, and this is okay. And it's okay also for G, because G is not virtual, so you can do whatever you want. So what you are doing here is that you are overriding a function f, because function f is virtual, and so you are declaring another function with almost the same prototype as f. And you are overloading G, because you are defining a different function G inside B, okay? And since it's different, you can do whatever you want with the return value. Here instead, this is wrong, because in class A I'm returning a reference to A, and in class C, which derives from A, I'm returning an integer, and this is not possible. Okay? So here what you are actually doing is probably you are going to run into trouble, and the compiler will signal you that you cannot do that. Okay? Okay, one important topic also is the topic of destructors and virtual destructors. And in particular, it may happen that at some point you need to destroy an object using a pointer to the base class. Okay? For example, in our shape example, I probably closed it, sorry. Okay, so in our shape example in the main, what we have is that I define an array of pointer to shapes, and actually I forgot that I need to delete them. So let's when I finish my program, I will delete all the objects. Okay, so this will just deallocate the memory that has been allocated here for all the objects. Okay. So what happens actually is that delete is passed a pointer to the base class. Okay. Now you have to be careful because in general, if you are not careful, this can run you into trouble. And in particular, here I'm really into trouble because I did not define a destructor. Okay, so let's define a destructor and let's provide an implementation for it. Okay, so I'm just printing something on the screen. Sorry. Of course, I don't need to write any return for the destructor. Okay, so I get a warning. So it's not an error, but it's a warning. Deleting object of abstract class type shape which has non-virtual destructor will cause undefined behavior. And in fact, the problem is that in main I'm calling the destructor with a pointer to shape. And so this is translated statically to calling the function for destroying shape. However, the object is not of type shape. It's actually an object of type circle, or type rectangle, or type triangle. So I'm calling the destructor of the wrong class. I'm calling the destructor of the base class and not the destructor of the derived classes. So if I try to run this, maybe it's okay, maybe it's not okay. Actually, in this case, it's okay. I don't get any real problem, but I'm very close to a real trouble because I'm calling the wrong function for destroying the object. So probably some memory was not allocated correctly, deallocated correctly. Okay, so the actual solution is to define the destructor as virtual. If I define the destructor as virtual, what happens is that the destructor of the right object is going to be called. Okay, just to give you an idea of what is going on, let's define a destructor also for triangle. And here I'm going to print what's coming out. Okay. I'm going to compile everything. Probably I didn't save, forgot to save all the file. Okay. So I have a problem here, pure virtual method call, and so I run into trouble when trying to destroy some object. So here, for example. Okay, so I really into trouble because I didn't do everything I was supposed to do correctly. Sorry, I'm just linking the wrong thing. Okay, so now it's correct. So okay, so I'm printing everything. The program works as before. When deleting everything, I print shape, shape, triangle, shape. So basically the last one is a triangle, so it prints first triangle and then shape. And this means that the correct destructor has been called. The correct sequence of destructor has been called here. Okay? And especially for triangle, it was the last one. If I do the same thing, for example, for circle, let's do another one. Okay, so circle, shape, rectangle I did not redefine, so it only prints shape, and then triangle shape. So now it's correct because the sequence of the destructor is called in the right order. If I don't put the keyword virtual here, instead I only print shape all the time, and this means that I'm just calling the destructor of shape. I'm not calling the destructor of triangle, destructor of rectangle, and destructor of circle. Okay, so this is in general a big error. So whenever you define a class which has a virtual function, please remember to always specify a virtual destructor for it, so that the hierarchy of functions for destroying the object is going to be properly called. Okay, so whenever you find you have a class which define a virtual function, also define a virtual destructor. So the destructor of the base class is called, which destroys only part of the object, the part, and even if not immediately, sooner or later you may end up with a segmentation fault or illegal access or memory corruption. To solve the problem, we have to declare a virtual destructor, so that if the destructors are virtual, the call is done at the runtime. We're using dynamic binding, and so these are called in the correct order. Another thing you should never do is to call virtual functions inside a destructor. Okay? So this is a very strange thing, so please never do that. You should never call a virtual function inside a constructor, because in the constructor the object is only half built, and so probably what happens is that you are going to call the wrong function, the one which you don't expect, because during construction the object is not yet ready, you are still allocating things. So the constructor should only build the object and not start calling dynamic behavior using dynamic binding and things like that. And the same thing is for the destructor. Okay, this thing is explained quite well in these two web pages, for example on Stack Overflow. Let's see the questions and let's look at the answer. So it says, suppose I have two C++ classes. Class A defines a constructor which calls a function fn. And this function fn is virtual. Okay? And it assigns n equal to 1 to member n. And then you have a function getN which just returns the value. Okay? And then you have class B which derives from A. Okay, so the constructor of B of course calls the constructor of A. And then you define a virtual function fn which assigns n equal to 2. So actually what is going to happen when you construct an object of type B? You construct an object type B, so the constructor of B is called, which calls the constructor of A. And the constructor of A calls fn. Now I said that when you call a virtual function like that from another member function, the virtual function mechanism is called. So which function is going to be called? This one or this one? So apparently one would expect that this one is called, right? N equal to 2. But instead this other one is called. And why? So the question is, one might expect that n is set to 2. It turns out that n is set to 1. Why? Okay, so this is the question that this user gives you to the asks to the community. And so this is the answer. Calling virtual function from a constructor or destructor is dangerous and should be avoided whenever possible. All C++ implementations should call the version of the function defined at the level of the hierarchy in the current constructor and no further. And there is more to it here in this fact. So basically the reason is that while constructing B, I first have to construct A. And so the constructor of A allocates memory, of course, and then calls the function. But at this point, B is not existing yet. The only thing that exists is the first part of the object, just the part that contains A. Nothing else. So this function actually calls this one, because it's the only function that exists till now. When this constructor is completed and I go and continue constructing the object, then this function is actually created. The virtual table for it is created, and so at this point I will finally have fn at my disposal. But at this point, during the construction, this function is going to be called. Okay? So this is probably not what you expect. Also notice that this is quite different from other languages like Java, because in Java what will happen is that the second function is going to be called, and so you may get into big troubles. I write about that also in a blog post that I wrote some time ago in Italian, so if you find it, you will find some more explanation. That blog post was about Java, actually. Okay, so never call a virtual function inside a constructor, and never call a virtual function inside a destructor, because probably it's not going how you would expect. Okay, so here basically we have the same example, and I can show you the example by running it, of course. So this is a virtual constructor, virtual function constructor. So you have a base class which defines a string name, and a derived class which defines another string name too. And this is the constructor of the base class, and this is the constructor of the derived class. And in the destructor of the base class, you are going to call getName. So in general, you would expect that the second one is called. But since we are inside the destructor of the base class, the derived class has already been destructed. There is no more name to around. And so what happens is that actually the real get name of the base class is going to be called. Okay? So in the main, I define an object derived of type, an object of type derived, and a pointer p to the base class, which points to this derived object, and then I print p get name, and then I delete p. So p get name here should return jack2. Okay, and when I delete it, I will get jack. So in the main, my name is jack2, and then the destructor name is jack, because the get name of the base class is called. So anyway, never do that. Even if C++ is safe and prevents you for doing stupid things, please avoid calling virtual functions inside constructors and destructors. So last thing today is that the fact that a virtual function is pure if no implementation is provided. And this is an example. And we have already seen into shape and already answered the question before. So fun is a pure virtual function. So this means also that class ABS, so abstract class, cannot be instantiated, while the derived class is going to finalize, so declare function fun, the implementation of function fun, and so you can define object of class derived. Okay. Why you cannot define object of class ABS? Well, it's quite simple. If you could do that, you could create an object of type ABS and then call function fun of it using, for example, a pointer, and then dynamically you will not find an implementation for it. Okay, and these kind of things cannot be checked at compilation time because of the virtual function mechanism, which only works at runtime. Okay, so the safe way of doing that is to prevent users from instantiating objects of abstract classes. If a class, so in general you can define only one function to be abstract, and for the other one you are going to provide an implementation. For example, in our shape example, class move I provide an implementation. Class draw, resize, and rotate I did not provide any implementation. So shape is abstract. If I try to create an object of type shape, of course the compiler will complain. Cannot declare variable x of abstract type shape because draw, resize, and rotate are pure pure virtual functions. Okay, so I cannot do that. So shape is abstract. When all functions defined inside a class are of type are pure virtual functions, and you don't have any data member inside, then that class is actually called an interface class. Okay, so an interface class is basically an empty shell. It's just a declaration. It just declares there are some function, but doesn't provide any implementation and doesn't provide any data member. Okay. What is an interface class useful for? So we want to use interface classes to specify that a certain class actually implements a certain interface. Okay? This is quite common in Java, and in fact in Java there is actually a keyword for indicating that a class is an interface class. Instead of writing class, I don't know, Jack, you are going to write interface Jack. Okay? In C++, instead, you don't have a specific keyword. You just need to define every single function as a pure virtual function and do not provide any internal member. Okay? This is quite useful when we are going to talk about multiple inheritance, so a class implementing multiple interfaces. Okay? So I just start talking about multiple inheritance, and of course we will continue tomorrow. So before talking about multiple inheritance, however, we have to talk to something more that has to do with inheritance, and in particular we need to talk about downcasting. So until now we have seen upcasting. Upcasting means I have an object of a derived type, I take its address and I assign it to a pointer to an object of the base class. So I'm going up in hierarchy, up because usually the hierarchy is drawn by drawing the base class on top and the derived class on the bottom. So it's reverse the tree. Okay? So upcasting because I'm going up in the hierarchy. Downcasting instead is when I want to go down in the hierarchy. So inheritance in general should be used when we have an is-a relation between objects. For example, a circle is a kind of shape. So this is called is-a relationship. Or you can say that a rectangle is a shape. Okay? So when you have this kind of is-a relation, then you can use inheritance. It's actually good to use inheritance. Now, suppose, however, that you have a derived class which contains some special functions that are useful only for those classes. For example, suppose that we need to compute the diagonal of a rectangle. Okay? So where do I put this function diagonal? I have two ways of doing that. The first solution is that I define diagonal to be in class shape, and this diagonal will just give you an error if it's not a rectangle, because it doesn't make sense to compute the diagonal of a circle or to compute the diagonal of a triangle. So you compute the diagonal of a rectangle only. However, we want to be able to understand if we have to call the diagonal by using a pointer to shape. So we put diagonal as a virtual function in the base class, and then we provide an implementation with an error in, for example, rectangle or in shape. So in shape, I'm going to provide an implementation which gives you an error. Cout error diagonal called on a shape object. Okay? So everybody deriving from shape is going to inherit this implementation and is going to print on the screen error diagonal called on a shape object. However, for rectangle, we actually redefine the function diagonal, and in the implementation I'm going to actually compute the diagonal as the square root of the squares of the two widths and 8. Okay? So what happens is that in the main, when I call diagonal on any shape, I get an error if it's not a rectangle. I get the actual diagonal when I have a diagonal. Okay? So this is the first implementation. The second implementation instead is I implement diagonal only in rectangle without implementing it in shape. So I just delete this. No diagonal anywhere. Okay? The only way I have to call diagonal is to call it on rectangles. But this means that if I have a pointer to a shape, before calling diagonal, I need to cast that pointer to a pointer to rectangle. Otherwise, I cannot call diagonal, because now diagonal is not in the interface of shape anymore. Okay? So I have two ways of doing that. If we put function diagonal only in rectangle, we cannot call it with a pointer to shape, because diagonal will not be part of the interface of shape. If instead we put diagonal in shape, it is inherited also by triangle and circle, and diagonal doesn't make sense for a circle. So we need to raise an error where diagonal is called on a circle or on a triangle. Okay? So, for example, we can put the function shape, function diagonal in the shape interface and return an error for the other classes. Okay? Or we can put it only in rectangle and make a downcasting when necessary. What does it mean to do downcasting? So, as I told you before, when you try to do casting, upcasting is automatic, and you don't need to do anything special. Downcasting instead is not possible, is not automatic, and in particular the compiler will give you an error. So let's take the main here. So here I was going to use a vector. We will see later on what is this vector. And I'm going to use the second method. So the diagonal is only in rectangle. And so I need to understand if I can call it or not on rectangle. So for doing this casting, I cannot do it, for example, in this way. So this is the C way of doing a cast. So VI is a pointer to shape. I cast it to a pointer to rect. Okay? So this is still okay, although it's not very clean. This is not okay instead, because as I said, this would be in the wrong direction, would be a downcasting, and so the compiler would give you an error. So let's verify that I actually have an error here. So invalid conversion from shape star to rect star. Okay, so this is a typecasting which is not allowed. I can force it using the C notation. Okay, and in this case it will not complain anymore. So everything works okay, the compiler does not complain because I'm forcing the casting. But the problem is that not every object into this vector, into this array, is a rectangle. So also a circle will be cast to a rectangle. And also a triangle will be cast to a rectangle. So how do I know that I'm actually a rectangle or not? In this way, I cannot know anything, because this casting will just copy the address into VI into R, and that's it, because it doesn't look at the actual type. I would like to have something that instead tries the cast, and if the cast happens to be good, it returns the pointer. Otherwise, it returns something different. So this is actually called dynamic casting. It's something new to C++, and you write it like this. So dynamic cast, then inside angular parentheses you put the type of pointer to which you want to cast, and then you put the pointer inside parentheses here. So this looks a little bit like a function call. Okay. So what this dynamic cast is doing is that dynamically, so at runtime, it looks into this object, and in particular it looks at the virtual pointer, so the first element of the object. And it goes and looks at which table is it pointing to. And the table is specific for each class. So the table contains information on the actual type, and this information is available at dynamic time. Okay? So dynamically we look into the object to understand what kind of type is it. And if we see that is actually a rectangle, then the pointer to the object is copied into R without any problem. If instead is something different, for example a triangle, then 0 is copied into R. So later on we can do a check. If R is different from 0, we call diagonal. Otherwise, we don't call anything. Okay? So this is safe because we are checking if we have a rectangle or not, and we are calling function diagonal only on rectangles. Okay? So dynamic cast actually means check. Here we have another example. So again we shape. F is passed a pointer to shape. I do a dynamic cast to circle. If C is equal to 0, then S does not point to a circle. Else, S and C point to a circle, and we can do something related to circles. So the dynamic cast is solved at runtime by looking inside the structure of the object, in particular by using the virtual function pointer to look into the table. And this feature is called runtime type identification, RTTI. And it can only be used when you have a class which has at least one virtual function. If you have a class with no virtual function, then dynamic cast cannot be used, because, as I said, there is some difference between classes which have virtual function and classes which have no virtual functions. For classes with no virtual functions are basically equivalent from the memory size point of view. They are equivalent to so they are basically equivalent to simple C structures. Instead, classes that have virtual functions inside, they use the virtual pointers to access tables. Okay? And so you can use this runtime type identification with dynamic casting only for the second type of classes, so classes that have virtual functions. If you try to use dynamic cast on a single class, simple class, then you will end up with nothing, because will not be possible. Okay? Also, we will talk about it more in detail tomorrow. You have several types of casting in C++, unlike C, and in particular you have this dynamic casting, reinterpret cast, static cast, and const cast. And every single type of cast has something slightly different. We are going to list these tomorrow. So tomorrow we'll come back, look again at this runtime type identification, and then we will continue with the lecture. Okay? So that's it for today. Thank you very much, and see you tomorrow. Bye-bye.